So the 2025 Nobel Prize in Physics was awarded to John Clark, Michael Davorate and John Martinez for the discovery of microscopic quantum tunneling and the observation of energy quantization in electric systems. To understand why the prize was awarded to these three people, you need to understand four key ideas. What is quantum tunneling? What makes this discovery special? What is energy quantization? And how they find this energy quantization in these electrical circuits, and what are those electric circuits are even. So let's first go and explore what quantum tunneling is. So what happened in classical physics? A particle can't cross an energy barrier if it doesn't have energy. If you take electron like a soccer ball, that is, you threw towards the brick wall, if the ball doesn't have enough energy, it will hit the ball and bounce back. It can never cross the wall unless it has enough energy to break it. So classically, no energy means no crossing. But in quantum mechanics, particle behaves like waves. So if you imagine a particle like electron as a wave and there is an energy barrier that is represented through this brick wall, because of this wave nature, a particle can tunnel through a barrier even if it doesn't have enough energy to cross it. This is purely a quantum mechanical effect, no classical explanation. But why does it matter? So quantum tunneling is usually microscopic, which means you see it in electron atoms. And what these scientists discovered that these effects like quantum tunneling and energy quantization can also happen at much larger scale, and that has big implications. So what makes this discovery special? This Nobel Prize recognized the first clear demonstration that the macroscopic object, something involving trillions of electrons acting together, can behave according to quantum mechanics. They showed that the whole electric circuit behaves as a single quantum object. A circuit can tunnel, the circuit energy can only take quantized value. This means quantum mechanics apply just not to particles but to large engineered systems, and these engineered systems become the foundation for quantum computing. So now let's explore how this whole circuit can act like a quantum object. But so what exactly this energy circuit is? So this energy circuit is Josephson junctions, which is the core building block of many superconducting circuits. It consists of two superconductors separated by this thin insulating barrier. So these are superconductors. These are cooled down to extreme temperatures, and electrons don't act normally in these superconductors. So if you look at normal metal, electrons move individually, constantly scattered, which create a resistance. But in superconductor, electrons form these Cooper pairs, and these Cooper pairs act very differently from single electrons. So what happened is all Cooper pair collapse into one coherent quantum state. This means that the entire superconductor share a single quantum state, and this quantum state has a wave function, and this wave function has a phase. Phase becomes the key variable in these junctions. So in this Josephson junction, what matters is the phase difference between the two superconductors, which we denote by this delta. So what exactly happens is the energy of this junction, which we denote as U, depend on this phase difference, and that become quantized. You can see in this figure you have these energy barrier. On the x-axis you have this U, which is the energy of the junction, and on the x-axis you have this delta, and you can see that it has some potential, and in these potential energy is quantized. It's not regular. It can only have certain energy values, not all the energy values. So this phase difference is the macroscopic quantity that behave quantum mechanically. So because of this junction has quantized energy level, the phase does not need to stay in one level. It's a superposition of several levels at the same time, and this is what quantum. So you can have the qubits which can stay in 0 or 1 at the same time. So what is exactly quantum tunneling in these junctions? So the phase difference in the junction sit in potential well, like a ball resting in a valley. Classically, the ball is stuck because it doesn't have enough energy to climb over the hill. But quantum mechanically, the phase can tunnel through the hill and appear in the next valley even if it doesn't have enough energy to go over the top. This tunneling event makes the junction escape from this zero voltage stage and produce a signal. This is microscopic quantum tunneling because it involves collective motion of many electrons acting as a single quantum object. So this formed the basis of quantum qubits because junction can occupy a superposition of energy state which we call qubits, and this is what they won Nobel Prize for. They showed that the macroscopic variable, this delta, the small phase difference between across the junction, can behave quantum mechanically, and this discovery is now the foundation of superconducting qubits used in today quantum computers, including those built by Google and IBM. For more videos, make sure you like, share and subscribe, and I will see you next time.